discuss model degeneracies. And then we will go through the exercise of spectral energy distribution fitting. So your model match to any data in broadband or high resolution. So I show you this part of a model calculation, which is published in this paper. The spectral resolution of this model is around 10 angstrom in the ultraviolet, 20 angstrom in the visual, and coarser in the near infrared. By definition, you don't need that high resolution here because you have broad molecular features, so you don't need to break them up. So it's clear. However, by the time these models were calculated, instrumentation were getting finer and finer. As I will show you, there is a little bit the prejudice that the more you look into a spectra, the more you understand. I will add that the more you look, the more the details you put in your spectrum matters, and if they are incorrect, that can be even counterproductive. But that was the thing. This is the spectrum of the sun, okay? And so you see the detail of lines that exist. In the galaxy, you will never see that because the features are broadened by the internal motion of stars called the velocity dispersion. We don't need to make this fuss. But in principle, what we would like to do also to understand the theory behind, this is the H-beta line, by the way, and all the things around, is actually we can make our model at higher resolution and then broaden them, hoping that we get all the information into there. So we want to use the same type of raffinatesse, I use a French word, that the stellar astronomers use to go for galaxies. Let's see what we do. So if you remember the structure of an EPS code, if the metrics are kept separately, as in my code, the only thing you can do in order to change the resolution of your model is to change this bit. It is actually much better. You keep the same energetic, possibly you even keep atmospheric parameters, but you may want to change that. If you remember the discussion on the apogee, it is actually matter which type of TA and log G I assign to that, having left this identical. So let's see what happened. You have done two choices, and I will show you some result. Your spectral energy distribution description can be either empirical or synthetical, okay? Theoretical means that you take a model atmosphere and synthesize the spectrum. Empirical means that you take spectra of real observed stars. In reality, both of them has pros and cons, which is interesting to discuss. So let's start from the empirical stars, which became very fashionable over the last, since the work of the Miles group in 2006. What is the big pros? You have real stars. So they, by definition, some absorption you see in them will contain all the effect that you would like to put in your model atmosphere, because it's the real stars. So problem like local thermodynamic equilibrium in atmospheres, you won't have it because you have the stars. But there are many cons, I would argue, and I will show you, that are quite severe as well. Because you get the real stars, you are naturally hampered by the fact that you need to observe these stars. Hence, you are mostly fishing in the solar neighborhood. The dwarf, for example, because they are faint, we would like to get dwarf far in the halo to get metal poor dwarf, as well as into the galactic bulge, where finally you would get dwarf that are as metal rich as our big ellipticals, but they are too faint or they are obscured. The other thing is that you get a limited parameter space. For example, our Milky Way lacks very massive stars. You have it in regions that are highly extincted, as was said yesterday, hidden in dust. So you get the spectrum, but you don't know what the actual intrinsic spectrum is that we need to put in the model. Abundance ratio that I will talk very soon, it's mostly solar scaled in the local neighborhood because it's the sun. And you would like instead to have a range to make your model flexible. The other things that this library, I forgot to quote the author, I'm sorry, would like to change, typically, you have mostly a coverage in the optical. All of these libraries that are very well known, and I've used them all, Miles, Stelib, and LOD, they cover from 3,000 angstrom, 3,500 to 6,000 angstrom. All the rich part of the near infrared is not yet properly covered, but we have this exception, valuable exception. Now, let's see what theoretical library can instead give us, which I really like. The parameter space is flexible. In principle, you don't know whether it is right, but you can model any star. You want to have a 2000 temperature, log G 5.6, right? A super dwarf in the main sequence. You run the code, you get it. You don't know if you put all the lines, that's the real problem, or whether you actual model all effects, but this is large, flexible, and especially is well-defined, which is the problem in the empirical spectra. In the empirical spectra, as we have seen, people give me a star, but I don't know the name and surname of the star. I have to apply a model atmosphere and get out the parameters. Here, the parameters are given as entry. They don't move, okay? If I want a 3,500 temperature, I get exactly that. However, the problem that remains is how well is my atomic description, molecular and atomic description of lines. People have, of course, put a lot of effort in that, but there are still regimes in which we see that something is missing. There are also type of stars that are completely uncovered by this model, like carbon stars, the one that I showed yesterday. They just don't exist. The model do very dwarf low main sequence stars with very deep bands, something beautiful to look at, but not the giant part. There are many libraries available. This is specialized in cold stars, so the real dwarf from very metal-rich but cold temperature. This is an improvement over the Kurux standard models. This is a Brazilian effort to exploit Beatriz Barbui code and to include different element abundances. And this is a high-resolution UV library that I will show. So for me, modeling, I experiment with them and see what is the output telling me. And this is done in this paper, which I believe is the only one that used them all. Instead of attaching to one specific calculation, I have calculated with my code the output population model as a function of the stellar library. In this plot, this is just shown for a 12 billion year population. The red one is a coarse resolution but extended in wavelength, because I will come back to that. The blue, thick blue, is based on Stelib. The maximum extension in lambda is here. The miles, that is higher resolution, is the green. And the LOD is the cyan. Well, considering that all these libraries, these three, are based on the same sample of, you see that there are differences. And these have nothing to do with my models, because the input is identical. The first two matrices are kept identical. What is different here is two nasty things. One is purely data. You may have mixed calibration at the edges. You see it going here, there are folds of fluxes. These are actually discussed in the paper. So if you know it, we also quote in which range you can use the library, the models with confidence. But the other problem is the fact that the Miles model have this shortfall of fluxes due to their assignment of parameters on the region branch, which is truly commented in that, and has generated a revision of this model. If you don't do it, the effect on galaxies is that you tend to get systematically older galaxies than with the other two models. It is discussed in this paper. So you see at which level of subtlety we are commenting. There are also regions in which here the agreement is very good. Good. So all the plots in this paper serve also to orientate at which point there is still work to be done on that. The library I mentioned based on Sloan 4 would like instead would like to solve most of these problems of discrepancies. Now, see the beauty of a fully theoretical library instead at its own resolution, which is, I think, 20,000. Yeah. So this, which is also in the same paper, using these theoretical marks, you get at anything, not a very young population, because these models are specialized for all the stars. So you actually have temperature only colder than like 8,000 Kelvin. So you can't model population with ages lower than 3 billion years. But when you do, you can have actually a tool, a double tool, in which you have a fully theoretical model and a fully empirical, and you can compare the results. Pushing into the ultraviolet, so what I show here is mostly around the optical. You can actually push this. I want to mention that because this is also published in another paper. What do we understand about the UV intrinsic spectrum of population? UV is useful in many things. At high redshift, this is what actually we sample, that is then shifted into optical. KMOS and these telescopes are actually looking at these things. In the local universe, you have all the UV from all the stars, and again, you need that. What we have discussed in this paper is the use of very high resolution models. These are from the library. The model is from the Kuruk's atlas, corrected by several authors, and what we have defined is a series of specific absorption, which are given like, because, sorry, this is from the paper, that are located at wavelengths that people can use and understand which parameter you get out. They are used in high redshift mostly. For example, the magnesium at 2800 is a redshift indicator even, not even an indicator of the population. The other thing I wanted to show you is that, again, you can compare to Magellanic Cloud clusters. Regarding your question yesterday, for the AGB, you use the 1 billion year cluster. For these things that are very young, you use the first two group of Magellanic clusters. Because it's an irregular galaxy, it's got a lot of star formation, you find clusters that are as young as 10 million years. Note the error bar, because these clusters are low mass. And so information fluctuates, but you still have a good handle to calibrate your models. What you see here are the model indices, the spectral indices. When you see the name in blend, BL means blend, meaning that that absorption is made by contribution of different elements. This is all discussed. While in certain cases you have a pure carbon 4, there is a silicon 4. Those you know. Others may trace iron or a mixture of it. So you use the cluster to check whether your model are anywhere close to the data. What we've done in this paper that is also original is to calculate two sets of models. The solid line are based on empirical libraries in the UV, while the dashed line are based on theoretical libraries. Because the argument, as I told you, was often, especially the UV is also complicated because of LTE effect. Empirical stars should be more robust, but you see, for example, look at this. For iron 5, which is important to trace abundance ratio in young galaxies, the empirically based model are far too strong compared to these clusters, while I would argue that the Kuruk's does actually a quite decent job in reproducing them. And you may find these things in galaxies, right? And so if you use the upper model, you would underestimate, you would conclude that your galaxy is lacking iron for some reason because the model is so much up, while another model with identical energetic would match. So the exercise of testing the model with star cluster, even if they are not pure simple stellar population, they will be because they are very young. So they dominate the light at 10 million years. So whatever is below, you even don't see it. In this case, it's easier. Still give you a good handle of how to use. Overall, the agreement was pretty good considering the regime. So this was the UV. Now, especially for Natasha, in your honor, I put a model that I actually calculated very recently. In fact, they will be published at some point. These are high resolution model in the near infrared. Here we are at 1 micron, 10,000 angstrom, 25,000. Using the IRTF empirical library, which gives me a set of stars that I can put in my modeling to calculate population generally older than a few billion years. You see there are some bands like the CO there that are beautifully shown, okay? These are good stuff. Huh? This is a tellurico. I don't know what kind of observational accident is there, but it's nothing to do with the model. You can't look at here. Over here, there is the C2 band of carbon. So this is essentially a new things we are exploring. She's going to explore first. I want just to show you how this compares with a fully theoretical library. And this is, we see, I saw it yesterday, so I still have to think about. But what I would roughly conclude is that there is a very good agreement here. Also, this is much higher resolution. While in this case, there is a mismatch, not if you calculate some indices, they might be even similar, but there is a difference in slope, which we still have to understand, right? I mean, this is theoretical and continue, while these are observed stars and they stop where the telescope stops. That is another thing. So there might be border effect there. Overall, I was pretty happy with that. So this is what you can do. These stars, this collection, as I said, empirical is good, but they don't cover all the parameter space. So I can model happily mostly all the population. And we will see what the future is going to reserve for us. Remember that there are instruments in making that will exploit the near infrared a lot. And that's why we are doing this effort. Now, behind all this line, there is a lot of chemical information. Now we want to try to actually exploit much better what is behind these things. Let us reprise this spectrum of a massive elliptical. There are many lines that you can use, broadened to the velocity dispersion, but still super evident. Look at the sodium D. So the question came up roughly 10 years, 15 years ago, due to a catastrophic discrepancy between data and model, of the following question. We measure lines. Lines trace elements. How do we know that in M87 the elements scale in the same proportion as in the sun? We don't know. We actually may think it's not. So all what I'm saying now, I will sort this later, but now we lose time if I do it, is to try to understand whether the chemistry embedded in this line can be actually positively extractive for galaxy formation. I hope you know this thing. And this is a good school text for transporting us from astronomy to chemistry, or the other way around. Now, we have many elements, but what the astronomers do is to call the hydrogen abundance X, that's fine. Then we have the helium abundance Y, and then all of this is Z. And this is what we put in the tracks. It is like that. Z in the sun is just 2%. Some people say 2%, and this is a matter-rich star. If you go to the halo, it's like 0.5. Yeah. But it is not true, because if I vary some sub-things around that, actually I get different lines and I get a lot of information. So what we want, what we started to do back in 2002 was, okay, now we change the model in order to reflect these things, and it's going to be fun. It actually took us to fantastic results, as I will show you, but the problem was to break up Z. There was a student yesterday who asked me what the definition of metallicity is over lunch. So I will back to that. But in principle, the total metallicity is Z over H. You can express, as we always hear, as iron over hydrogen. And the fact that people do that is because you see iron lines. But iron is not too close to total metallicity. Actually, oxygen would be much better, okay? And our stellar friends know this very well, but you need to transport that. So indicating galaxy in Fe, saying that the metallicity, this is not fully correct. So we'll see what we have. As I said, there is an indication there was to many people, and this is just a more recent compilation, that what we call alpha over iron. Alpha is oxygen, magnesium, silicon, calcium, so the alpha type of elements, where alpha is the helium-4, over iron is a ratio that encodes a very important information, namely the contribution of supernovae type 2, which release mostly alpha, over the contribution of supernovae type 1a, which release instead iron. The supernova 2 release a bit of iron, but it doesn't matter in this concept. They dominate that. So in the Milky Way, now forget about this bulge thing, which is incorrect here, should have been there. We know that this ratio varies with iron abundance such that the halo of the Milky Way is very enhanced, we say, alpha over iron 0.4, and at some point this ratio decreases to go to the sun, where the ratio is 0. How is this interpreted in galaxy formation term is crucial. We conclude that the halo has been formed fast before it could get polluted by the long time ejection by supernova type 1, which are explosion of low mass stars. Okay? If you don't see iron, it means there was no other stellar generation after that that could incorporate the iron remnant. So the chemical evolution of galaxies is super robust in this sense, because this ratio, once you fix them, they won't change. While colors evolve, you follow the model to see the evolution, the abundance ratios stay as they are. In the disk that has been forming star, I told you yesterday, as a tau model for 10 billion years, obviously the abundance ratio decreased, not because alpha changed, but because the iron went up. And so we have a solar scaled abundance ratio. So in principle, already in the Milky Way, we see different locations. This is Eileen Tolstoy is an expert of dwarf galaxies, and this is what she was putting there. So you got even subsolar because of the huge extent and length of star formation. To keep you hot, I will show you that the biggest elliptical are consistent with that, which was really a surprising result when we found it. But let's first understand how to do these things. So what we want to now to modify are the effect of non-solar abundance ratio on this line. So the first paper that highlight the discrepancy between data and model is actually a cosmology paper by Daniel Einstein, who is one of the bosses of the Sloan 3. And he was mostly doing baryonic acoustic oscillation, and then he got interested in galaxies, and he took models that were available at the time, and he plotted model lines, you see H delta. These are just lines in the absorption, okay? You don't need to go so specific, but you see that there were some lines that were catastrophically, some data in some lines that were just off the model dramatically, and you cannot make any error to reconcile that. And so then Eisenstein put out the thing that Guy Worthy put out in '92, that the most massive elliptical did not match standard models. And so the question was why they didn't. Because in principle, the most massive elliptical are those whose spectra show the best defined and thick absorption line. So the expectation was exactly the opposite. The star-forming galaxy that do not show much of this line would be off, but not the biggest elliptical. So in order to cure that, what we have done, that was the first attempt, and now we have a robust model for that, was to modify the abundances in the actual absorption. Here, just to show you what we do, suppose you have this absorption, which is probably an iron line. Around your absorption, you have, this is a stupid example because I have two lines, but forget that you have only one. You have here the continua, And here you have the absorption that is due to some element. Remember that only hardly you have one only element that causes that absorption. In reality, there is contamination, okay? And the only way to understand that is to take a model atmosphere, because the data won't tell you that. But what we did was to modify both the inference of this absorption in both the continuum and the line. And let me harass you with a few equations, but you don't need to look at that, but only see the principle. Suppose you want to modify the strength of the carbon 4 line, okay? What we have done here is to consider the partial derivative of what we call the new index as contribution, as additional contribution at the varying the element abundance we wanted to check. So suppose we want to check is a full chemical evolution model. So we have all the Z that I showed you before. Some elements won't matter at all, others will matter more. I started with varying magnesium in lockstep of 0.3 dex, suppose. I remeasure the index of my model atmosphere, and I see what is the effect, differential. I calculate the partial derivative, and that is the mini contribution that goes into my model. And I can do this for overabundance and underabundance. At the end, there is a very nice compact formula that we put here that actually tell you how to vary. How the new index will be a function of the old index, which is at the end the product. We do this at constant solar metallicity, and someone at lunch yesterday asked me, there are other people like Riccardo Schiavon who modify the indices, not exactly as us, but especially they don't fix Z, but they fix iron. We instead produce a full Z over H grid, where inside that pot we change all element abundances. If you have any questions, stop me now. I know these things can be, but you don't need, sense it. It's obvious that if I wanted to make a model where carbon reflects a non-solar ratio, the first things I need to do is to evaluate how much this index changes when I change every ratio. Correct? I hope it's so. So, we have done this. Let's keep this slide, and let me show you the result. Now, this plot shows 3 series of models. For convenience, expressed as iron and magnesium line, but the lines are stellar population models, as I showed you yesterday. The blue line are for solar scaled ratios. This line is for an enhancement of +3, so a factor of 2 over solar, and this is +5. You see that increasing alpha enhancement, you mostly decrease the iron line, which is obvious because alpha enhancement is mostly an iron depletion more than an enhancement of alpha. Yes. But it's good to say because you think alpha enhancement, you increase the alpha, but if Z has to remain constant, you have to decrease mostly. Yeah. So, and what you see is that indeed you have a variation, so that was good. But what we plot here, most importantly, are the data. So these are data of the biggest elliptical galaxies, okay? From the Faber sample. And you see these points were indeed off solar scale models, as Dan Eisenstein found. And then instead they start to be to match the grid of alpha-enhanced model. What was fun to see is that the population of our Milky Way bulge, which people like Beatrice Barbuy told us already they are enhanced, they indeed follow the 0.3, the plus 0.3 alpha enhancement, and nicely match to elliptical galaxies. All over the metallicity, this point contain Ortolani et al. Bulge globular cluster. So what do we take away from this? Big elliptical galaxy did not follow a chemical evolution that give them solar scale abundance ratio. This to me, which I grew up, I'm older than you and I heard a lot of messages, is one of the reasons why you cannot make an elliptical by merging 2 spirals. People know this very well. But the chemistry will fool you. You certainly cannot make, this is the reason why we come back to your point of yesterday. If you merge 2 disks and you can even do this at ratio 1, their abundance ratio is already sub-enhanced. If you merge them, the enhancement is not an additional term. It comes from the explosion and the stellar generation. And that's why in the simulation of chemical evolution that Darren Crotton, I don't know if he showed yesterday, but I will show you something, the elliptical, in fact, do not have the right abundance ratio because they form through merging all over the cosmic time. And these things, already without putting any modeling, tell you that they are offset. And they also tell you that actually they have more or less a constant iron, and what varies is magnesium, meaning the time scale is really similar. So this is a strong cosmology result that is posing problem to lambda CDM, so derived from abundances of stars. I will come back to that. And this is the way it became famous, but let's go on. So we were very super satisfied about these models. The first things we did was, again, to check the model with globular clusters, according to the good tradition in which you want to understand whether, before going to obscure galaxy, you can make simple lines. These are all indices that I can extract from an optical spectra. You see also situation in which the models are too low. You are this yesterday. So, for example, the sodium D, one would like to trace the sodium abundance, but the sodium D is affected by interstellar emission more than the stars. And so the discrepancy we find here, actually, is because the model do not contain any re-emission. Okay? So, in fact, we caution in that paper not to use or not to abuse this index for stellar population analysis of all population. But there are other indices that are extremely well behaved. The thing that we have done now was, okay, we discussed how to derive metallicities of galaxies. The best way is to use models which allow for this flexibility. And what we have done is to reproduce the metallicity scale of Zing and West. And I want to stress why we choose this one. So, using our model, these are globular clusters in the Milky Way. 47 TAC was highlighted because the referee wanted exactly us to show the position of it. This is total metallicity as a function of the measured scale from spectroscopy on red giants. Okay? And you see that they actually match lovely. If you derive metallicity with models without the flexible abundance ratio, the data will be off the scale. The reason why we use this instead of the Carretta and Gratton who is coming in the room, and it is fully explained, is because they have done a super homogeneous scales, but in iron. So it's iron. Why we want to trace that? Because this is what comes from the stellar tracks. These guys publishes iron. This is something that you find in our paper. What they do is an average of magnesium and iron. This is alpha enhancement. That's why it works. But it went on for 20 years, this ambiguity. It was actually their work of Raffaele and Carretta showing that there was this tension also, while we were showing this in integrated light. Which tells you also, when you compare something to model, make sure you are comparing really oranges with oranges. It seems stupid to say, but there are so many ambiguity if people don't tell you exactly what they measure. Of course, iron is an electron donor. It has the strongest line in the spectrum. It's much easier to measure. Okay? But typically, an evolutionary model will give you this number. So, fine. Questions? Because I will come back to that when we do galaxies. I would suggest that we conclude here this part saying that there are these models, they allow flexible abundance ratio. They're being calibrated in both the indices with globular clusters and the metallicity scale, such that when you apply them and you find numbers, you are at least secure that you are locked to the metallicity scale of real clusters in the Milky Way. Okay? Good. Don't sleep because I'm changing topic. Now, let me jump. I'm sorry, but I had to include that because it's important for the masses of galaxies. The other thing that you use the model with is not only to calculate the light contribution, but you need to have mass. Everyone calculates stellar masses of galaxies. So I want to show you, for the first time, what we predicted, for the first time for you, I mean. Instead of evolving light, let us evolve mass. And I recommend you this review that we wrote for Modern Physics a couple of years ago. It's called Galaxy Masses, and I wrote the part on the modeling masses, but there is a lot of dynamics, lensing, dark matter. So that's crucial to the dark matter. So this is what, when I evolve my population, I said the stars die. So if I start at 0 age, so when the population is born, my mass is the total. And then the stellar mass start to decrease. Do you agree with that? Good that you know. Do you all agree? Why do the mass decrease? No, okay, so they decrease because the stars die, and their remnants has a mass smaller than the initial. If you keep an evolving, a constant mass when you model galaxy over the redshift range, as unfortunately it is often done in the literature, you are going to find a mistake, okay? Because your mass, whatever you do, doesn't matter whether you merge or not, is going to be less for the same stellar population just because the stars have died out. And the gas, and this is another mistake that is circulating, gas is not contributing to stellar mass. It's gas mass, which is another thing. So this plot shows you the evolution with age of stellar mass for different assumptions regarding the initial mass function. You remember yesterday I put the integral, I assume something. So these are like Milky Way mass function. These are the ones really supported by data at the moment. So this tells you that over 15 billion years, your population will have roughly up to 40% less stellar mass due to passive evolution of the star. Can I tell you something? 10 years ago, the fraction of dark matter in galaxy was roughly 30%. Okay? So it was identical to the fraction of remnants. I'm ironizing that, but it was because people were using mass to light without this account. Okay? Now the situation is being understood, but still, as you can imagine, if you change the IMF at leisure in your model, you can see that if you assume a top-heavy IMF, top-heavy means that your population is made by massive stars, they evolve very fast. They leave you a lot of heavy remnants, but the stars, you lack 60% of the population. Then you measure the dynamical mass to light, so with velocities, and you see that you are missing mass. Instead, if you assume that your population is bottom-heavy, as it is done nowadays for elliptical galaxy, well, your mass doesn't evolve. Bottom-heavy means the population is made of low-mass stars. Low mass. Ask you why it doesn't evolve. At least some of you should be able to answer this question. Now I do like my students. Now I wait, and so I will go over time, Lori. You don't want to have a go. I tell you simply, if I put bottom heavy means my galaxy is dominated by low mass stars. Low mass stars. So why, passing the age, this mass doesn't change? Or change very little? Perfect. Is the length of stellar evolution is very long for low mass stars. So they never leave the main sequence, they don't die, so everything stays where it is. And that's the reason why with this super heavy IMF, Corroy, Van Dokkum, etc., found these results, which may be correct, that in fact, but we knew this, you don't need dark matter in elliptical galaxy. There is no dark matter there, okay? And it is quite robust change in that. On the opposite happens if it's there. That's a fast evolution, so your population fades away. Let me give you another cosmology example. Galaxy formation modelers, like what Darren Crotton showed you yesterday, sometimes they push for a top-heavy AMF to get galaxies very luminous, because these galaxies are made by massive stars. What's the problem with this? They disappear shortly. So you can do the sub-millimeter galaxy redshift 2 very bright, but then they will fade away because the massive stars die. Okay? So they remain actually much smaller and hidden in the universe. So the choice you make here is interesting, but it has got implication on the larger scale, which is the thing we like. So it's not trivial. Here I wanted mostly to show you, because this was requested by students of another school, it's nice. When your population is emitting these remnants, they wanted to see the partition between black holes, neutron stars, and white dwarf. This is shown here for a group IMF. For other IMF, you would change it, but a little bit. This is the total amount of remnants, which at the end, in this case, is 15%. You remember before, it was roughly 40%, the total ejecta. And you see how it works. Black hole are emitted over here, then their contribution don't change, because the massive stars are all dead. Okay, good, thank you. If you make a continuous star formation, this will increase, of course, because you put more massive stars. White neutron stars kicked in when you have 40 solar mass at the turn-off, and then they also don't change. The contribution of white dwarf instead followed normal evolution. So this is going to increase secularly. These type of things are now used to understand which galaxy are the best producer of gravitational waves, because you need to have this. You need to have them in the first place, so a bottom-heavy AMF is not good for that. And then you also need to merge them. Just an aside. Okay. Yep. So the planets are not included in this calculation in the sense, but one could extend that. They don't give us light, as I said yesterday, so the integration down is stopped at 0.1 solar masses, even 0.08. What you should do to put what I should do to put the planets would be to integrate from what is the minimum planet mass. Let's approximate to 0 respect to a star, up to 0.1, without light contribution. Yeah, could be fun to do it. It's not there. It is not there. One would need a mass distribution for planets. We heard from the first lecture is an efficiency of 1/5. Yes, so one could actually, it's not there, but one could have the fun to do it. Okay, and it would only contribute to the mass, of course, and not to the light. Thank you. Okay, now, let's see a little bit of this. Several of you, even if you're only students, master, or undergrad, told me you are already doing this exercise. So suppose this is a general problem. Suppose you have a series of data and you want to match a model on it. How do you do it? I tell you, it's not trivial. Now, this you see is my poor rendition of my model. It's not that. But there can be a situation in which you actually pretty decently match this data and you have one, we call it offensive outlier or whatever. What do you do with it? Now I'm trying to make it, but what do you do with it? You either think this plot has a lot of meaning and your model is crap, which could be, or you think this plot, you sigma clip it, which is what I recommend. Because, you know, there is some regularities. 5 feet and 1 is not there. That doesn't tell you the whole. It could be an emission line. It could be a bad weather. It could be a cosmic ray. I don't know what else I can invent in observation. So what do we do, actually? So the thing we want to discuss together is the following. How many points you need to constrain the models? And it's not trivially the number of wavelength points you have. How many models do you want to use? The more, the happier, we would say. But sometimes you use models that you know a priori, like the indices that we discussed yesterday. Maybe they don't give you exactly the information, they produce more noise. And the other thing that is also much discussed is, do you impose priors? A prior could simply mean, we discussed with you the red t-shirt yesterday, which physical model you use, that's your prior. You decide to make a prior on me, so you use my model, or you use BCO3, that's already a prior. They are not, as you said, they are not identical, so this is like making, you can make priors. Prior may be beneficial, you just need to say what you do. So the first thing why it's tricky to compare model to data is something that is known since decades, but I wanted to remind you for the student, the main effect that you have in spectra is that there is a degeneracy between age and metallicity. People hate that, the observer. But this degeneracy is stellar evolution, intrinsic in the temperature and metallicity effect. It's not that you can take it out. It's only proving that the models are correct. And it's telling you that a young population or a metal-poor population here at this stream will have similar SED because one is luminous and has opacity of electroscattering and the other doesn't have metal. So these things are well understood. The other problem is, this is a sketch of running age. From 10 million year to 1 billion year, there is a strong evolution. From 1 billion year to 10 billion year, much less. This is, however, redshift 2 to 0 in a passive elliptical. So getting an age in this mist where the evolution is mild is quite complicated. In terms of chemical composition, you see how different an identical age give you if you change metallicity. This is a very metal-poor population, typical of Milky Way halo. 10 billion year is a hot, pure black body. Okay? Sometimes you read in paper, the galaxies have all the same metallicity. Then you go which metallicity they fit. 1. Yes. So if you assume, so it's different, right? You can assume solar metallicity, proceed with your analysis, then the only thing you get are different in ages. Okay? In practice, you would like to constrain both parameters. And I want to show you one thing to break the age and metallicity degeneracies, which was stated by Guy Worthy, is to extend the wavelength range. And this is something, in fact, is a message I want to leave you. So here I compare two of my models. The red one is 2 billion year old, metal rich. The black is 8 billion year old, solar metallicity. Within this wavelength range, this is log, but this is the range of the Sloan. Well, they are just identical. But if I put galaxy formation at 2 billion year, I go to redshift 0.2, maybe. 2 billion year and look per time. 8 is redshift 1. I mean, it makes a difference when Darren is telling you that his galaxy form a different redshift. In order to constrain, you need to decide. What we put forward was that if you extend the near-infrared, the 2 billion year population is actually redder because of the AGB stars. The old, no, it has a red giant branch, but it's not so red. So after this, in these decades, actually most people tend to use also near-infrared to better leverage your degeneracies. And now comes really what should you do? In general, I will say a few rules of data. I still advocate a longer wavelength range, but maybe I just drop this. Don't use far infrared to constrain models. I see Natasha is, yeah. Over the K-band, you have dust re-emission, PAH, and all those other accidents. You can use them to constrain your solutions, if you get a dusty solution or not. But it's very risky to include the points in a model fitting, because the part of the dust is much more model parameter dependent than the part of the stars. So I don't think it's worth. That's my opinion. Try if you want. You get a lot of degeneracy. There is a code that is doing that, MagFIS, by D'Acunha et al. They fit everything. But if you see their contour, the solution is not very well constrained. That's my, yes. Now, why did we go to high resolution? Now you see, because you think here there is this degeneracy that it is really the 3/2 rule is confirmed also by my model, because we don't have a high resolution model to check. And maybe if you have a high resolution, you find lines that are different. In this paper, instead, we show that the age metallicity degeneracy remain even at high resolution. So the reason for going high resolution is not to remove a degeneracy that has to be there, but it is to determine abundance ratio. That's the best way of doing it, but not because of degeneracy. I just want to show you this, which is a provocative plot we put over. These fits are all obtained with my models using a cluster in the Milky Way, which has a nice turn-off age of 3 billion years. And this is the exercise I told you yesterday. So I fit my model, their spectra, I should obtain something close to 3 billion years. So this is the best fit solution that I get in my model version based on this stellar library. Spot on. And I put all the grid in. If I use this stellar library, I get that the cluster is 9 billion years, half solar metallicity, which is the age metallicity degeneracy. Exactly that, because the chi-square are basically identical. I put them for fun, because these numbers are meaningless. But this is a problem that the people doing large galaxy survey have. I can look at my fit one-to-one if I fit one object, right? But if you have, the dark energy survey has millions of galaxies. I'm not sure we could find a student that would look at each age metallicity and stellar. Well, the galaxy zoo people have done a little bit of that. This is just to say we want to have an automated method to select the best solution that is not just the chi-square, okay? In this case, the chi-square is a bit better, and this is really the right solution. But if I only fit with Milesh, I would get that. That fulfills the thing that I said before, that using model based on this library tend to give you older galaxies. It is demonstrated with the cluster. And we know this age is not 9 from the CMD fitting. So when I buy in Sloan 4, the same thing, running all galaxies in Sloan 4 manga with both, because there are Spanish people who absolutely insist for having that library. I whisper my opinion, I'm sorry, but this match to me is a killer, okay? There is something we need to revise on that. There is another degeneracy you want to consider, that is the degeneracy with dust and the star formation mode. And here I show you another plot, which is all model, okay? And I vary the parameter tau, which is the length of star formation. Yesterday I showed you the tau models. And the t, which is the time at which I look at the galaxy, how it look like, okay? And this is wavelengths, as always. So, you see that here I have a moderate tau, but a young age. And here I have a much longer tau, but an older age. And these are the CD that you give. Actually, the longest tau, but the old age dominates to give you less luminosity in this sense. If I decrease tau very small, I get nearly to a single burst, which is what you see here. At 1 gigayear, this is the green line, which is radically different from the blue. So the message is, what do you want to get out of your galaxy? Ideally, you would like two parameters, the length of star formation and the age, which tell you the distance from the start, okay? Yeah. However, look what happens if I put the dust on the long star formation, is the red line, okay? Essentially, I diminish this part. This dust has to come out somewhere there, so it is a good check to check. If you only have this data, it's very hard to distinguish. And this is something people know. Sometimes you think, oh, I have a young dusty galaxy. Instead, it was an old, or the opposite. It was an old galaxy which has red light. And again, this tells us we need a longer wavelength range. So after years of bothering with this problem, because also when you do the models, first of all, there will be a large amount of people writing you email. How do I do that? What do I fit? No, it's good, but it's science also, that one, the application. So I need to think about. Sometimes you got into black channel that you determine nothing. So I have sort of collected a sort of rules which I found useful, but you'll have to see. So the first thing is, that's because it's a lecture on stellar population model. Do allow your population model to change, but don't do it with models that have identical input. We discussed at lunch yesterday, because variation there would mostly tell you about the noise in their model, mostly, than in the physics you want to derive. And I have a plot in that. I still think you should use a wide wavelength range, simply because you have seen that the different stars weight a different wavelength. So you want to actually try to get the whole picture, avoiding region where we pull in all the physics. And this is like in the dust. This is very important because people are keeping making the same mistake. Do not oversample. And this is also in your poster, Natasha. I was pleased that we got the same result. You think that getting finer in a short wavelength range is the key. And people do this with photometric redshift, but not for the physics of galaxies. Because essentially, you give too much weight to a wavelength range, and you risk, and she has actually proven that, to overweight a model that is penalizing the other wavelength range. It's very perverse. This was started by Combo 17 in 2000, where they have 17 narrow band filters, all in the optical. It was to avoid the spectroscopy, that is very expensive. And then they derived properties of galaxies that sometimes were all optical, okay, no infrared. So I show you that. This is we can discuss it over coffee, it's a bit tricky, but it became custom, especially in our redshift Cosmos survey. When the data don't fit, you use a model to apply offset to the data. Fine, but then you fit a different model and it doesn't fit. Mazing et al. 2010, Crick, Conroy et al. 2010. They have done exactly this. So we can discuss. Now, priors. For the AGB yesterday, I put all the models I could imagine, okay? So it was generous because I was not being willing to find that the AGB would win. I would leave the galaxy free to fit. So if you instead assume you know your galaxy already, this is a concept of post-starburst galaxies, then you're putting a strong prior on your solution. And if your fit is not within that regime, what would you conclude? You don't know. So my attitude to liberty would suggest that use a wide range first, then put the priors after that. Sorry, this is repeating because I pasted and copied, forget about. For alpha enhancement, we will see, you should use lines instead of full spectral fitting. That is not yet mature for that. Like the leak indices models with alpha enhancement. With alpha enhancement in the model, otherwise you won't get it. But for determining age, and this is a defense to all our redshift studies, broadband, to me, is as good as high resolution spectra. So we can go cheaper. So if we want to determine alpha over iron, we don't need the high resolution spectra. But if I want to know whether the population at redshift 2 is 1 or 5 billion years, broadband CD fitting is fine. This has been demonstrated. And so when I am on attack of a telescope and I read proposal like we need the spectroscopic age, no. You don't need the spectroscopic for the age. You need it for other things. You will have these slides, so we can, I overshoot a couple of minutes, yeah? Because there was a discussion yesterday. So let's show explicitly why the physical property of data depend on model. The people keep finding and keep wondering. Instead, the solution is very simple. Imagine you have these 5 points. You have 2 different models. It's quite clear that when you fit them, you will get different results. This is a plot that shows us how to do it. This is a galaxy. All these points, look how much information we have emerging. Spitzer with Hubble Space Telescope. Up to here, 1, 2, 3, 4. These are the Spitzer channel, which sample gas frame near infrared of your galaxy. And these are the HST. What actually mostly Emanuele Daddi did, and then of course we wrote the paper together, was to leave a huge amount of models, so no prior, nothing at all, fitting separately, okay? So the result he got with my model is that the galaxy at this redshift is 0.4 billion year, which is good actually. Basically a single burst was giving the best fit, metal rich, and no dust, zero dust was necessary. With these other models, he got the same age, which was quite interesting, right? And it's due to the fit in this part of the spectrum, which we said is more age sensitive, but quite a substantial reddening. Also, the near infrared was off, and it's the same thing I showed you yesterday. Now, here the grids are identical. What did we do in order to see whether there was more parameter space in the blue model to perform better? Was to allow ages older than the universe. You would tell me, why do you do this crap? No, I told you, it's not that I am a believer in faith of the age of the universe of 13 point. Also because over my study, that has already changed. You know that after Planck, the universe is a bit older than it was before. I mean, it's like that. So if I keep following the cosmology tweaking, instead, let's do this exercise. But people didn't like it. But in any case, then your galaxy, the blue galaxy, in order to match the near infrared, it needs to be 2.6 billion years. Now, the problem is not only that it's older than the universe. Let's say that it's as old as the Big Bang. You need to make your galaxy. These are nearly 10 to the 11 solar masses galaxies. The universe had the Big Bang, dark ages, reionization. When do galaxies form? If you ask Darren, you don't get fluctuation down to redshift 3 for this massive galaxy. So the problem here is that you have a drastically different result on the galaxy formation. I'm saying this because what I dislike, and I think Gustavo is with me in this, when people use our model, then they make a sentence, the model are uncertain. And so they don't publish ages. Very often they are like this. They just publish the result of the fit and the stellar mass. And this is not really what one should do. If you bother to do the exercise to fit the model, believe to all parameters you get. Discuss them, because some may be incorrect, but to trash them away and to just retain what you like, not you guys. So the stellar mass is incorrect. So here, again, you can retain this best fit if you like. This is, many people do, but you get a different, for example, star formation history, a tau model, that's okay, but the metallicity is super low. There is no galaxy in the local universe that is 10 to the 11 solar mass metal poor. There is a mass metallicity relation. So, finally, constraining the age of the universe, we can find the relative best fit of both models. This has not changed. And this is now 1 billion year, but still with a lot of reddening. And give you this fit here, which may be within the statistical broad chi-square is identical, but give you two different epochs of galaxy formation. In this case, a very different stellar mass. The problem with this object was that the Spitzer channel of far infrared did not detect any dust in this galaxy. This is what I mentioned yesterday, but for this it was calculated here. So you would say this solution, and it's not because it's this solution with a lot of reddening, is not good. It seems to fit your points here, but when you calculate the integral of the re-emitted bolometric due to dust, you would have a peak that the data have not seen. So when I say why the wavelength range, do the exact fitting in the thermal wavelength range of stars, so up to the K-band rest frame, but use all the other information that is abundant nowadays to scream away solution, if you have them. Do you want me to stop? Yeah? Perfect. No, perfect.
Thank you, Claudia. Question for Claudia?
Taking advantage, I have the mic. Claudia, my question was concerning what you said about the worry about using the infrared. I know other people might be wondering about this statement that you made, because very often, I mean, I assume that you don't, I mean, there are certain parameters that certainly you require further infrared, like luminosity, dust temperatures, and all of that. I mean, your statement is strictly to determine metallicities, or you think that?
No, it's not to determine, it's the tool you use to fit those data. So let me specify my statement, and thank you for that, I should specify. No, it's not for determining age. The statement is the emission from stars, we know pretty well, and we make a stellar population model from the UV to the K-band, okay? Longward K, you have the Rayleigh-Jeans tail of the coldest inert stars, and they don't give you much information. But what you have then is the re-emission by dust, okay, in different phases, all complication, hot and cold. This has not much to do with the bulk of things that make these models. Dust and shrouded TPAGB, people have tried to put it, Dan Kelson primarily, on top of my model, and also Charlie Conroy. But the lifetime is very short, and we have a poor calibration in the Milky Way. So again, what do you gain from there? So my message was only forgetting the main physical properties like age, star formation history, metallicity, if you have high resolution or here, a sense of it, just fit up to the K-band rest frame. However, use those other information in other sense. You mentioned the star formation rate. That is absolutely right. We did that with Emanuele Daddi using the star formation rate I derived from here compared to the far infrared indicators. These are very important. Or, as I said here, you get a very dusty solution. Do you see any dust in the far infrared? So there is a huge richness in using our data, but I think fitting like you fit other wavelengths is still risky. Radiative model have been published, Granato, Silva, these people, and Magfis. They use all these it's complicated, and you increase the number of parameters, to me, with marginal benefits so far. This is only what I wanted to say.
My question is about, well, in fact, the first part of your lecture, when you were talking, you're saying that instead of iron, perhaps the oxygen would be much better to be a metallicity indicator, and yeah. I bet that this has to do with the way we're measuring, if it's the gas or the stars. But I don't know, I would like you to explore more, because then it's not that clear.
No, oxygen is the main contributor to total metallicity in the chemical evolution model. That is the thing. Not measurement, the opposite is quite tricky to measure. Exactly, but because iron is much easier to measure, with cleaner line you go for iron. But theoretically it's oxygen that dominates. But if you have a full model, you can correct. So you give me your iron, fair enough, then I put it on the model, I can still scale it. But it's not an observational thing, it's rather the opposite. So the alpha, oxygen, and magnesium are very abundant. They are closer to the total Z than iron, especially in alpha enhancement population.
Yeah. No, I was mentioned because if you use stars, for sure, oxygen, it's, you go to iron, it's easy to measure. But if you go to the nebulae, whatever kind of,
Yeah.
it would be the opposite. So the one you get, really, you can measure quite well, it's the
Yeah.
oxygen. So,
Well,
and you
that's
need to
good, though.
compare, and this is what I do, so it's a really nightmare when you need to compare the two because of this.
Well, because you need to have the partition of all elements. And it's true in other phases you see different elements, yes. Mm. Yeah.
Hi. Well, I'm one of those who try to fill the full spectrum using just the optical wavelength. So that's
High
it.
resolution, high resolution.
Yeah. So I will try to work with the near infrared too. But a problem that I usually find, or not a problem, but I have a doubt, because I have worked with PPXF and Starlight, that kind of programs.
But I was running out
Yeah.
of time.
Sometimes the single star populations grid that they propose to use, I think that the grid is too large, or there are not many options, mainly in metallicity, for example. And also, I also have always the question about, for example, when I'm fitting global clusters or elliptical galaxies or lenticular galaxies, how large is the uncertain in the thing that I'm not considering alpha versus iron enhancement, and I wanted to know what is your opinion about using that kind of programs, and how better should be the grid that we use in the single stellar populations.
Yes, so yeah, it's a long, it's a good point that I promise to expand more tomorrow. We can look at that. You touch upon the problem that now the data are high resolution or most IFU survey, so you would like to fit the full spectral fitting. That was in my talk, so tomorrow morning we'll do it. But the full high resolution model, included mine, do not include the abundance ratio variation over the full SED. The few that have tried that, like Paola Coelho, have remained the difficulty of matching some indices like DH beta. So, in fact, what you still could get out of those exercises is a determination of age, because that is also sensitive to the slope of the continuum. A code like PPXF, I use something that I don't like, which is called regularization, which is really, it was done for dynamics, because you want to confine, is a sort of optimized synthesis, as I described yesterday. You don't bother the physics of your galaxy, but you want to get the velocity. So you regularize your solution, which means you trash away things that don't fit, okay? It's okay for dynamics. It has been extended now to use for stellar population, but we know, I mean, Michele and I work together in Mang, is not good for that, and can give you results, the parameter space is not adequate. Starlight is better in this respect. You can talk to Natasha, who's used it a lot. What it does with respect to the code we use, that I will present tomorrow, is that it imposes a bit of prior to use only discrete grid of age and metallicity model to start with, which I don't think, I mean, you don't need that. And then, if you have a larger grid, you would be able to fit globular cluster of galaxies. That is what I show here, actually. This is with the same grid, because this is a very important metallicity degeneracy. This is obtained with a full spectral fitting code. It's called Firefly. Forgive me, the acronym is stupid, but I'll tell you where it comes from. So this is, it took all the models with all age and metallicity available, and it gets the right result, okay? For that, in that case. The problem is, I said, these are semi-empirical, and PPXF has the same charging. It might have the Vazdekis model, but it's the same. Not all library cover a squared age and metallicity grid. Fine. So if you fish a theoretical model, then you have a complete pot that you can fish out the solutions. But if you use those, for example, Stelib exists only at solar, subsolar, and 2 solar. no low metallicity. So you can't, this is a metal-rich globular cluster, but you would not be able to fit the metal-poor globular cluster. I have a lot of things to discuss on this topic, which we can maybe do a bit later. Yeah.
Claudia, you spoke about overfitting. Of course, there are statistical methods to avoid it. For instance, to consider the covariance matrix. Are these applied to these observations?
So they are, the covariance matrix is a thing that we are discussing in Sloan 4, more than me, Michele Cappellari, Matt Bershady, and these people, based on results on PPXF. In this case, we have used a sort of, in this, but I will speak about tomorrow, a Bayesian cut. So we retain all the solution, all the chi-square, independent of their values, and then we cut them to take only the most significant, but being quite generous, okay? Fitting all the solutions. So it's not Bayesian in a sense, but it gives you contour of probability. In the high redshift sense, you can't do much else than considering the probability distribution function. This is done for each solution, because you have a limited number of points, a wavelength point. In the best case, you have 14, as to the high redshift galaxy that I showed before. In manga, you have all the pixels and this IFU. This type of matrix is being considered. I must admit that is a bit, go a bit outside my expertise, because sometimes I have the feeling that a fit works just by looking at it. All the stomach type of feeling. While if you put a lot of statistics, sometimes you can get a little bit misled. But I agree with velocity determination, this has to be done. It is being done. Not in all cases of codes. For example, Starlight doesn't do that. It's probably a more simple type of chi-square cut. But the overfitting, you know, sometimes, yes, you oversample a region. Yes. Is it what I, let me see if I found that. The evidence of it, I agree, but I don't know why people do that. I had it here. Yeah. This is the Perez Gonzalez et al. Oversampling of this region here for a cosmos. And you miss, here we show the models a different redshift. You miss actually most part of the CD, okay? So in order to catch up, they have linked with other filters, but still when you fit the model, you get, you overweight the oversample model. So what we show in this paper is that instead this evenly distributed set of filters that are not that that thick works better, and we have calibrated this with mock. So the mock would tell us that that was the right answer. I cite your poster because that she put outside, because she found the same thing, according to what she weights in real spectra. So I agree with you. My primitive approach was mostly not to do complicated statistics, but to use common sense, to use only data with a fair sampling all over the wavelength range, but not something like that. But I'm sure I didn't answer your question because I'm not good in statistics. And
so you were mentioning the different IMF and the impact that it has on deriving the stellar mass. Could you give us like a quick conclusion? You were mentioning the bottom heavy IMF is mainly used for ellipticals, but what will be your input on that? What are you using, and what should we use in the end?
so I will explain tomorrow why the bottom heavy IMF is not used for elliptical, but Koroy van Dokkum claimed to have found that near-infrared spectroscopy of sodium is so deep that require to use model with the bottom heavy IMF. In the old time, old is until a couple of years ago, people have always experimented with these three IMFs, okay? There is hardly any difference between Krupp and Chabrier. If you are French, you use Chabrier. If you were studying or working in Germany, like me, I started with Krupa, but I have also Chabrea release, and they are hardly different, a bit in the remnants, as you see. So these are IMFs that you see, they exist. So the first thing would be to try and fit those. The thing is that your spectral model is not very sensitive to these IMFs because they are very similar, and because we learn that the main given by the turn of mass, which is weighted identically. Okay? So people do this exercise and you will find hardly ever any difference. But you see the difference in the mass exists, of roughly a factor of 2 between these two, okay? 1.6 is. So you take the freedom, you will find identical fits between a normal and the light, the bottom light. You will find a lighter galaxy. You can correct it with a factor, even without redoing the fitting. Things change when you change the AMF a bit more drastically. Are these motivated? Honestly, yes. Now this seems to be what some date of elliptical require, so it would be applied to the center of elliptic, but we know our Milky Way bulge is like that, and there people have counted stars. Top heavy, I never seen any top heavy in the local universe, but is useful, seems useful at high redshift in semi-analytical models, because otherwise you don't get the high luminosity for these galaxies. So this is more a theoretical try. This is something that, if confirmed, is quite catastrophic for cosmic galaxy evolution, but I will put some caveats. And these are things that we know. You need to decide whether you want the IMF to change all over the universe. Do you want that? Or no, in fact, it's quite ugly, right? Because if the IMF changes for each galaxy, then we should stop making prediction. If the IMF is ruled by gravity, I think it remains the same pretty much in every location, and that allows us to make models. This allows me to say that we are organizing a Royal Astronomical Society special discussion on the IMF, okay? The 10th of November in London. These events are super posh because there is the Queen, you know. But I understand it's expensive. It's 1 day of full discussion, but with all the major experts in the field. So I give you the detail later, because if I understand the trip to Brazil for 1 day is, but if you are anywhere close to in Europe, that would be a very good thing. Good.
Thank you very much. So we can stop here and go for the coffee break. Thank you, Claudia. Just a quick question, a quick announcement. So we're going to have the poster session, but I don't know if I mismatched something, but the only poster I have for today is Natasha. So if some people send me the poster and I didn't collect it, or if you forget to send it and you want to give it to me, we can do the poster session this afternoon. So Natasha, this afternoon. Thank you. Enjoy the coffee break.